Hello, let's look at magnets because I've borrowed some magnets from school and I need to give them back tomorrow, so I need to do a little video about them. Okay, so these red things are magnets. What do magnets do? Well, magnets will attract each other. They exert a force on each other, and they'll exert a force on each other even when they're not touching. I can feel them pulling together like that. Okay, so they will attract each other across the desk. It doesn't matter which one I push together. It attracts the other one. But what else will they do? Okay, if I turn this one round, they will push as well. They will repel. It will push away. Okay, and let's try this end. Okay, this one will repel that one as well. Okay, so these are magnets. They will push and pull on each other. There's a song about that, I think. What about these bits? Okay, I took these off at the beginning. Are these magnets? Well, they don't actually seem to be doing anything. They seem to be pieces of metal, but they're not attracting each other or repelling each other, to be honest. So, although I can pick those up with a magnet, they're not themselves magnets. They're not doing any attracting or repelling themselves, but I can pick them up. And you notice I can actually pick them up with either end of the magnet. I can pick it up with that end or that end. That's given me a clue that at least one of these things isn't a magnet. Okay, because if you have two magnets, then they will be able to push each other like that and spin around. Okay, so we have an idea that these are magnets. So I'm going to put these down. So that is it's a pair of magnets. These things, they are attracted to magnets, but they're not actually the magnets themselves. They're not doing any picking up. Okay, what about some paper clips? Okay, paper clips. Again, the paper clips are not picking anything up, but if I take one of these magnets, I can pick the paper clips up with it. Okay, so we say that these are attracted to magnets as well. Okay, so these are not magnets themselves, but they are magnetic. Okay, so these pieces of metal are magnetic. So are the paper clips. Let's see if these iron nails, I've got an iron nail here, see if that's a magnet. Oh, might be a magnet. Let's see if this paper clip is a magnet. No, this iron nail appears to be already a magnet, not terribly strong. Let's see if another one is. No, this one's not. Okay, so this iron nail is not a magnet, but it is able to be attracted to a magnet, so we say it's magnetic. And actually this one is also able to be attracted, but this one is a very weak magnet of its own. I don't know if you can see that. It is picking up the paper clip. It's not terribly strong. It's not as strong as the others. It won't pick up those. It will attract to them, but it won't pick them up. So it's not as strong as this magnet, but it is a very weak magnet. That's something which can happen to magnetic materials. You can turn a magnetic material into a magnet somehow, occasionally. So these nails are not terribly strong magnets, but they are magnetic. Let's have a look at another couple of materials. Okay, I've got a Coke can here because I was having a can of Coke. Other drinks are available. This is made of aluminium. Okay, let's see if that can be attracted to. Well, let's see if it picks up these. No, it's not a magnet. It's not picking up the paper clips. Let's see if it will be picked up by the magnet. Nothing. Okay, no effect whatsoever. So aluminium, although it's a metal, is not magnetic. Okay, so I'm going to say that it is non-magnetic. Let's see if we've got any other things that are non-magnetic. Okay, I've got a piece of circuit board. You can't really see very well, but that's got copper. It's got copper tracks running on it. Let's see if that can be attracted to the magnet. Nope. Nothing. Okay. That's not attracted, so we'll call that non-magnetic as well. And I've got a Sharpie, which I might use later. Is that magnetic? No, that's sort of plastic. That's not magnetic. Piece of wood. Is that magnetic? Nope. Non-magnetic. Put that in that part. Whoops. Put that in this pile. Put the Coke can over there. And I've got some tweezers. They're not magnetic either. Okay, so they're not acting like a magnet, they're not magnetic. So not everything is magnetic, but things that are magnetic, sometimes we can make them into magnets. And some things are magnets themselves. This is what we'd call a permanent magnet. It is a magnet all the time, it's permanently a magnet. Okay, so that's a little bit about what things are magnetic. Let's look at about some of the properties of magnets, because notice that when we put the two magnets together, some ways round they attract, and some ways round they don't attract, they repel, they're trying to push each other apart. Okay, like that. Or if I turn it round, those are pushing apart as well. So there's obviously something different about one end of the magnet compared to the other. And, well, one thing that's different is it's got a hole drilled in it. Okay, but is that the only thing that's different? Okay, it's got a hole drilled in it. That's not making a difference, that's just showing which end of one of the magnet is which. Because if I put the two ends with the holes drilled in together, they repel each other. If I put two opposite ends together, they attract. If I put the two ends without the holes together, they also repel. Okay? And if I swap them over, they attract. So there's something different about them. Now, on a whim, what I'm going to do is, let's put this somewhere out of the way. Put it over there. What I'm going to do is see if I can find a way of hanging this up to see what it will do left to its own devices. Okay, because I have a hunch it's going to do something. So what I've done is I've made a little stirrup for it to sit in, and a piece of cotton I can hold on to it. Let's see if it'll go in the stirrup properly. Okay, I want to hang it up like that. So what I want to do is take my little stirrup and put the magnet into it. It's just a loop of wire, I just needed something to hold it. Okay, so that's holding the magnet, and then the string is going to let it swing and see where it comes to rest. So if I hold it and see what happens to it. Okay, well the problem is, because it's on a piece of string, there's not very much friction, there's not very much air resistance, and it's just swinging around, and it doesn't seem to ever want to stop. So I'm going to just slightly modify what I'm doing and bring in something to give it a little bit of friction. So I've got some water, and what I'm going to do is do the same thing again, but this time I'm going to swing it, or let it swing, and then I'm going to put it in the water to damp out the swinging. Okay, so if I put it in the water to damp out the swinging, there we go. Okay, so it's pointing that way. Now let's see if I take my magnet and I'm going to spin it around the other way, and we'll see what happens. Okay, so I'm going to spin it, put it in the water, hang it on the string. Okay, put it in the water to damp out the swinging, and it's turned itself around. Okay, so just in case it was the string, I'm going to twist the string a little bit between my fingers to try and make it turn that way. So I'm going to make it turn that way and then see what happens. Okay, can we see what's happening? Okay, so it's pointing, once I let it settle, it's pointing that way. Okay, it's as if it's pointing sort of that direction, approximately, maybe that direction. Okay, so let's see what the other magnet does. Okay, I want to put this quite a long way away from the other magnet because they do tend to attract each other, and that's going to affect it. Let's see. Okay, this is the other magnet. I should have put a dot on it because I've put them both out of the shot so you won't believe me. But this is the other magnet, it's dry. Okay, so let's put this into the stirrup, and okay, and we'll hang it up like that. So I've got the one with the dot is this end. I'm going to hang it up and we'll put it in the water and let it do its thing, see what it does. Okay, the only reason I've got it in water is just to damp it down, because otherwise it just swings backwards and forwards forever and it'll just take forever to stop. It's going to stop pointing that direction. Okay, if I let it do its thing. And I happen to know that that direction in this house is approximately towards north, okay, towards the North Pole where the polar bears live. Right, let's tidy up a little bit because it's getting a bit messy here now, so let's get rid of that. Let's wipe this down. Let's wipe the magnet. Okay, so both of these magnets, when I hung them up and let them swing and then gave them a little bit of friction from the water to make them slow down a bit, they both ended up pointing that way. Then actually, if I was in school, then we would be here, and north in real life would be that way. Okay, so that would be the map showing north. This would be lined up with the ground. So these magnets have lined themselves up with the Earth's North Pole, pointing this end towards the polar bears and this end towards the south, which would be where the penguins are, and sort of Australia direction. So what would make sense, I'm going to label them with the direction they point. And I'm going to call it, this points towards the North Pole, and this points towards the South Pole. And on this one, okay, that's the one with the dot, this one points towards the North Pole, and this one points towards the South Pole. So each of these magnets, I'm now going to say it has a North Pole and a South Pole, or more correctly, a North-seeking pole because it points north, and a South-seeking pole because it points south. And this one has the same, has a North-seeking pole and a South-seeking pole. So magnets, oh, I'm using the wrong pen, using a proper pen. Magnets. Okay, they exert forces, attract or repel, and they have a North Pole, which is a North-seeking pole, and a South Pole, a South-seeking pole. So we shorten it to say South Pole, but we actually mean it's a South-seeking pole because it will point north. If we hang it up, the North-seeking pole will point towards the geographic North Pole, where the polar bears are. And the South-seeking pole will point south, where the penguins are. So that's the main things we've done so far about magnets. We've also found that there are magnetic materials can attract to a magnet, okay, and non-magnetic materials don't. Okay, some examples of those, e.g. paper clips, okay, iron nails, and things that don't were aluminium, copper, wood. So that's the main things we've got about magnets so far. Let's just see with these poles which way things attract. Well, it's fairly clear that it's looking like north and south attract each other, and south repel each other. North and south attract, north and north repel. Okay, so if I put them together, north, south, they all stick together like that. So we have opposite poles of a magnet attract each other, and same size, same type of pole, so like poles, we call it, repel. And this idea of hanging up a magnet and seeing which way it goes gives us a very useful use for a magnet, which is a compass. Now I have to move these magnets quite a long way out of the way because otherwise they'll affect the compass. If I bring in my compass, this is when I use orienteering, it's pointing in that kind of direction, which is the same way that the magnets were pointing when I hung them up. And if I turn it around, it stays pointing the same way. The reason I don't use this one anymore, it's got a great big bubble in it, but it's got water in it for the same reason I was using water. If it didn't have water, then this needle would swing about wildly. This needle is just another tiny magnet. It's been magnetized so that it's got a North Pole and a South Pole, a North-seeking pole and a South-seeking pole, and then they've put it onto a little spindle bearing. Not sure if you can see it very well in there. It's a tiny little bearing. That means it can pivot and swing around on that central axis, but the water then just prevents it from swinging wildly backwards and forwards. And if I take a more normal looking compass like this one, okay, you can see that's pointing the same way as well. The red end is pointing that way, the white end is pointing this way. You can't see, but there is liquid water inside there. The reason you can't see it is because it hasn't got a bubble in it, which is disrupting it. This one doesn't really work very well anymore because the bubble gets in the way. And if we have that red red end of this needle here, this magnetic needle, that must be a north-seeking pole. and we have north poles attract to south poles. So this south pole of this magnet is attracting that needle. And if I spin this magnet around, the north pole will attract the south pole. And we'll see that happen as well. Okay, so the north attracts the south, and the south attracts the north. And I can move it around like that. Okay, but now it's pointing back that way. So if it's pointing north, there must be something in the Earth that's making it point north. So if we imagine what the Earth looks like that, and I'm standing on the Earth with my compass, okay, this is not to scale, okay, the compass needle is pointing that way, okay, and that's the north end of my compass needle, and the south end of my compass needle, oh, should I have drawn that a bit bigger? Maybe, let me see that, okay, I've got the north end of my compass needle and the south end. That north end must be being attracted to something, and the south end is being attracted to something. It's as if at the top of the Earth, so here's the Earth North Pole and the South Pole. So here's the polar bears. I'm not very good at drawing polar bears. That's a polar bear. And here's a penguin at the South Pole. Okay, polar bear and penguin. It's as if there must be a south and a north. So this north attracts to that south, and this south attracts to that north. So inside the Earth, it's as if there's another magnet, but the wrong way up, with the South Pole at the North Pole and the North Pole at the South Pole. It sounds stupid, but it's the only way that actually makes sense. And the alternative, if we had a north-seeking pole at the top here, would be that every compass, we'd say that, oh, that end, we're going to call it the South Pole because it points north, which doesn't really make any sense. So we call this end the North Pole because it points towards north. And it just happens that there must be inside the Earth a magnet, not a real magnet, not like the red ones that I've got, but something that's magnetic, having a south, what we would call a south pole at the top and a north pole at the bottom, which seems the wrong way round, but it's the only way to make it work. This magnet inside, it's not exactly lined up with north, it's approximately lined up with north. Actually, the north magnetic pole, well, the South Pole, which is at the North Pole here, is somewhere over Greenland. It's a little bit offset. But if we're far enough away from the North Pole, then it's pretty close. And actually, this does move around a little bit, this magnet, not because it's a real magnet, but actually it's because it's caused by swirling currents of moving molten iron in the Earth's core. You've probably done in geography that the Earth's core is made of iron. Some centre is solid, but there's some that's molten. As that swirls around, it actually creates a magnetic field, which the Earth has, and it makes it look as if the Earth has a magnet like that.